x times the log of a. This is what is going to be really formula. So it's going to be, this is going to be n naught times 2 to the a, 2 to the t times log 2 actually. Okay. This would be really the population. Okay. This is the way, the rate at which the population is changing. Now let's put some numbers and ask some questions actually. So imagine that in the beginning when you started observation there are 100 bacteria actually. Okay? And you want to know the growth of the bacteria after say 4 hours in a culture or in a slide or whatever, after the 4 hours. So what you need to do, you need to compute. So what does it mean? So I want to know that how much the population is changing at t equal to 4. What is the rate of change in population after the 4 hours actually? Obviously, the more people you have, okay, so the more bacteria you have, they'll produce more actually. So the first population is going to be pretty slow, but then it's going to shoot out actually. So like the COVID-19 cases actually, first there were very few people, there was a very rapid growth actually, there was slow growth. So there were like 10 people, 5 people, 8 people a day that you were finding. Okay, and it took, for example, 2 months or 1.5 months to cross, say, for example, 1,000 positive, cases for COVID. But now, since the number has gotten bigger, so the total is, I think, 65,000, something like that, positive cases. So the rate at which now, for example, the COVID-19 cases are increasing is much higher actually. So previously in 1.5 months you had 1,000 cases, and now you have more than 2,000 cases every day, and this will go on actually. This will go on. So this dP by dt is telling you what? So it's making a prediction actually. So once you have this formula, it's making a prediction. So in other words, imagine that this rate of change is the rate of change of the COVID-19 cases actually. And you want to, say for example, know that after the, what do you call, say 90 days or 90 hours or 900 hours, so what would be the number of, at what rate the cases of COVID-19 would change and increase actually. They'll grow. So what you just need to do, just substitute, t equal to 19 it, and you're going to have a prediction about the rate of change in population actually. Though this is not a good model, I'm not saying that this is a good model. This is a very ideal model actually. So there are lots of things that we are missing in this model. For example, if the bacteria, grow, okay, they die also. So you need to, remove actually those from the rate of change in population. Anyway, so there are several factors that we should encounter that we should incorporate in a good model. But let's talk about this ideal model actually. So I'm interested in at what rate the growth would change after the t equal to, what do you call, 4. So it's going to be, so you need to do what? You need to substitute, say 100 times 2 raised to 4 times log 2. So the number that comes out is 1109. Okay. Now what is the interpretation of this? The interpretation of this is that this much of bacteria are growing, the population, the rate at which the population of bacteria is increasing is this. In other words, on average, there are 1,000, so the population of bacteria is growing as 1,109 bacteria per hour actually. So this is the number of bacteria per hour. Okay, but you will see that if you substitute, for example, t equal to 10, this rate will go away. In other words, the more and more bacteria will grow per hour. So this is not like this is fixed actually. So as time passes, the population of bacteria will grow. Okay, so you can take an example of, for example, virus actually. So a virus infected your computer. So it makes copies. Now you have, for example, so if you had 100 viruses, okay, 100 copies of the viruses, for example, in your computer, okay, it will make, that 100 will, in next instant, they will make, for example, copies thousands. So there will be 1,000 copies after some unit of the time in your computer. And if you do not do anything, that 1,000 will become, hundreds of thousands and millions and billions actually. Okay, and eventually everything will die out. Okay, so it's a good model. So what we can see here, that the same derivative that was modeling different things in chemistry and physics constant is now modeling things in the context of what you call biology. Okay. Another example that I would like to do, say from biology, is really the blood flow in the vessels actually. So I'm interested in knowing that what is the rate of the blood flow in the vessels actually, in the human vessels, say, okay, period of time. So imagine I have a blood vessel. So let's assume blood vessel to be a cylinder. Let's assume it to be a tiny cylinder actually, and the blood is flowing through it actually. Let's assume that the radius of this cylinder is capital R. Okay, so the radius of this cylinder is capital R, and now here's the interesting thing actually. So think about it. So go to the river or the canal that is nearby you, and see that how the flood, how the water is flowing in that canal or the river actually. You will see that the water that is in the middle of what do you call middle of the river is going to move more faster as compared to that water that is on the banks of the river actually. And why this is happening? Obviously there is a friction actually. So the banks kind of banks of the river kind of create a resistance in the motion of what do you call water actually. And the more you are moving away from the bank of the river, the more faster the what do you call the water will move at. So same is the case here. So if the blood is flowing through this vessel, okay, the blood that goes through the middle, through the axis of the vessel is going to move faster. Okay, so here the blood is going to flow a bit less faster, and here it's going to move really slow actually. Okay, really slow. So here the blood is flowing in the vessel more faster, while here on around the surface actually the blood is flowing slower. Okay, so here is a model actually. So there's a beautiful model. There is something what do you call the law of the laminar flow. It's called the law of the laminar flow. Okay, laminar flow is simple flow. For example, the water that flows through your pipe actually when you are watering your garden. Okay. Let's add some more things. Let's imagine that the length of this vessel is L. Okay, and let's assume that okay, this distance from the middle is really R. So R could be any distance. So in other words, if you are at this distance, okay, the blood will flow faster, but I am here, the blood will move, what do you call, a bit slower, but if I am here, the blood will move more slower, and if I am really close to what do you call the surface of the vessel, then the artery, then I am going to move really, what do you call, slower. So imagine so small r is kind of, if the distance of a point is of an arbitrary point in this vessel from the middle actually. Okay, so imagine I am at some point here, which is at some distance from the middle. So it's not the surface, it's not the, what do you call, this middle axis, but it's somewhere in the vessel. So it's going to have so at that point, what would be the velocity of the blood? So it could be anything. Okay. So what does the law of laminar flow says? The law of laminar flow says that the velocity of the blood or the velocity of the fluid in such situation can be given as P over, I'm going to write in a moment what all these things are, P over 4 eta L times R square minus small r square. You need to keep in view eta, L, they are fixed, P is also fixed, the radius of the vessel is also fixed. So the only thing that is changing is this small r. So the V is a function of r, so it depends on r. Okay. So the velocity of the particle, the fluid particle, the water particle depends on that how much you are away from the surface or from, what do you call, the central axis actually, the middle axis. Okay, or this line, this middle line. Okay, and this is the law. So P is what? So let me say that eta is the viscosity of, what do you call, fluid, or here it's blood. So eta is the viscosity, say for example, of blood, and P is the pressure. P is the pressure between endpoints from P is the pressure difference between the ends of the tube, between ends of this artery, vessel, tube, whatever you call it, slender, doesn't matter, end of the tube. Okay, and L is the length of this is constant, the radius is constant actually. So now what I would like to know? So I would like to know that if I, for example, in this vessel give you two positions, say R1 and R2. Okay, I made a bigger one actually. So imagine a zoomed version of it. So imagine I'm in this tube at location R1 and another location R2, while this is really what we call the middle axis. And I want to know what would be the average change in velocity So I know that okay, maybe R1 here and R2 here, okay. I know that, you know, the blood moves the fastest here, a bit slower here, and a bit slower here actually. Okay. So the more nearer you get to the, what do you call, surface, your speed of the blood depends on that, how much you are away or close to this, what do you call, middle axis actually. Okay. So if I want to compute the average change in the velocity, so what would be the average change in the velocity here? So average change in velocity is going to be V of R2 minus V of R1 over R2 minus R1. And if you want to compute, for example, the change in the velocity gradient, the instantaneous velocity, this is average, not average velocity, but average change in velocity. But say you are interested in, what do you call, instantaneous change in the velocity. So if you want to have the instantaneous change in the velocity, you need to compute a limit. That would be, either you can compute a limit, delta R goes to 0 and delta V by delta R. So if you have been given a formula for V, so you can compute the derivative of it. So when you're going to compute the derivative of it, so all this is like a constant. This is like a constant and minus R squared. So it's going to be P over 4 eta L times 0, because the change in R squared over the R is 0, minus 2R. Okay, this is what it is going to be. And if you compute it, so you're going to get what? You're going to get P over 2 eta L R actually, so dV by dt. So this would be the rate at which the velocity of the particle, not T, this is not T, sorry, this is R actually. The rate at which the velocity of blood is changing when you are changing the position in the cylinder actually, okay? When the small r is changing actually. And the negativity shows that as you move away from, what do you call, as you move away from the central axis, this middle axis, okay, the line of the symmetry, axis of the symmetry, whatever you call it, okay, the velocity would decrease, it will become negative actually, okay, provided that all these are positive. These all are positive, okay. So as r is changing, the velocity of the blood will decrease actually, okay. So as you are moving away from the middle axis, the velocity of the blood is decreasing. So you can see it from here as well actually. Okay, as you are moving away from this central axis, the velocity of the blood flow is decreasing actually. So this would be the case. So for example, one practical example could be that imagine you have say let's talk about humans. So you take a small human artery, okay? You take a small human piece of artery or rug of human actually. So for that, the viscosity can be taken, viscosity of the blood can be taken as 0.027. These are experimental, these things can be found experimentally. And let's assume that the radius of that artery is 0.08 centimeter. Okay, and so the length of the whole artery is 2 centimeter, and say the pressure between the end points of the artery is say what do you call 4,000 dynes per centimeter square. So there are different units for it. 4,000 dynes per unit centimeter square. Okay. So now, what would be the velocity of the particle at, for example, a distance that is 0.08. So let's take, say, r to be 0.0, say 2. Okay. So 0.02. So it's like you are how much away from 0.006 units away from, or maybe, yes. So you are pretty closer to what you call the central axis actually. Okay. Because if this total distance is 0.08, then 0.02 is going to be somewhere here. Okay, so what would be the, for example, velocity of the blood at this radius actually? So you need to substitute, say, 0.02. So you have all data, substitute it into your formula, and you will see that what did you get is, what do you call, 1.11 centimeter per second actually. So this is what, and the velocity gradient, so the dV by dr, by substituting the values, you're going to get as minus 74 centimeter per second per centimeter. So this is really going to be so what would be the interpretation of this actually, 0.74 centimeter per second per centimeter. So what does this say? That if you drift yourself, say if you are moving away, say 1 centimeter away from, say, for example, this middle axis or the axis of symmetry, then the velocity of the blood will reduce by minus 74 centimeter per second actually. So if your velocity is really, for example, in the middle, say 100 centimeter per second, or say 100 centimeter per second, and you move away, say 1 centimeter from this middle axis, then your velocity will remain 100 minus 74 in 26 centimeter per second. So just by a single drift, 1 centimeter drift, your velocity is going down by minus 74 centimeter per second. And if you, for example, drift 1 more centimeter, the blood will almost stop actually moving. Okay. So what you can see from here, okay, so my point is not just to solve these practical problems, but to give you a feel that how a single notion of derivative can many things in different contexts actually. So if you take a context of biology, it can mean, for example, the velocity, the rate at which the blood is flowing through vessel. So it can also mean that the rate at which the bacteria are growing, the viruses are growing. If you take, for example from the chemistry, you can have this derivative can model what you call isothermal compressibility. It can model many things, and similarly in the case of the physics. So what you can do, so when you are solving what you call your practical problems through the machinery of differential calculus, you need to spot that, okay, which two quantities are depending on each other, and what is the law that relate these two quantities actually. So if you have a law that relate these two quantities, you can easily compute, the rate at which one quantity is changing when the other quantity, the independent quantity, is changing actually. So I'll carry on the discussion from the next, and this is the end of what we call the third chapter. So the next discussion we're gonna start the chapter number 4 of the book actually. So I'll be a little bit fast actually. Thank you.